Hi everybody and welcome back. Well, things are getting back on track now. I got a new TDA chip ordered for that little Class D amplifier, so that should be in this week. I have that little bare bones board coming in, the little computer board, so we should have our computer back sometime. But more importantly, we got our new boards in, and as a little added extra, since I was placing an order, I also sent these in to have some nice ones printed up, which is that capacitor board that replaces that little can capacitor. So I think this looks a lot neater than the homemade one that I made. So here it is. It looks just the same as the one that was on the last video, other than the collector and base is now in the correct position. So now that we have everything, we can start installing some components, kind of like we did on 2 videos ago. So let me get started again, and as soon as I get some progress, we'll be right back. Well, here's the first one put together. It turned out pretty good. Hodgepodge of resistors, but of course that's what I had in stock, and they were the ones that were best suited for where they are. They're the correct values, and there's some of them are kind of overkill. They there's some 1% precision ones in there that really don't need to be 1%. They only need to be 5% or so. This here, this 22, is actually in your bias circuit with this transistor. This is a known transistor or resistor that can fail. This is actually a 2-watt metal film resistor, so it's very tough, and I doubt that it'll burn up. All of these are metal film, so they should hold up very well. And that's it. And by the way, I did do a little bit of testing on this heatsink. Before I put this together, I took a resistor and I coupled it to the heatsink with heatsink compound, and then I applied enough current through the resistor to dissipate approximately a little over 3 watts of heat. And just so you know, if you do the math and add these up, this plus this plus this dissipates a total of right around 2 watts, so at the most. So running this heatsink at 3 watts, it barely got warm. It didn't get very warm. It got warm maybe about, I don't know, 77 degrees Fahrenheit. And I left it on for about 20 minutes, and it never got any warmer than that. So I think this is a good solution, and it will be able to dissipate the heat of all these very well and stay cool. So this one's done. Turned out okay. Again, as far as I can tell, it's correct, but won't know until we plug it in and try it out. But before we do that, we have to build the other one. I'll get that put together, and then we'll come back. Well, there they are. The 2 boards completed, and I guess now it's the only thing left to do is to test them out and see if they work. I checked these things multiple times, but no matter how many times you test things, you just never know if you miss something. I went over my biggest concern was the transistors, to make sure the pinout was correct on them, and I'm fairly sure now that they are. But you know what happened with these guys. So everything's put together, ready to test. We're going to get the amp back up on the bench, and well, you'll see with me. We'll see it. We'll find out together if this thing's going to work. Okay, just a crazy little thought here. I have 2 amplifiers in front of you right here. One is the McIntosh, and the other one is this. And it's hard to believe that this little chip is rated at 160 watts per channel stereo from 20 to 20,000 hertz at 10% distortion into 4 ohms, which is not great, but think about it. If you ratchet that down, you go to an 8 ohm load. This is 105 watts per channel into any load. But even at 8 ohms, with low distortion, this is still a good 50 or 60 watt per channel amplifier. And look how tiny it is. Look at that. That's how far we've come. I mean, it's kind of crazy. And we can argue about all the pros and cons of Class D versus Class AB, all these different things, but it's just cool that they're able to come up with something like this. Just a thought. Anyway, let's get back to our project. So the first thing I did was I just took a little file and I kind of knocked off these corners. They were really sharp corners. You can see how these ones are. These were like that too. Just kind of rounded them a little bit to make it a little easier to plug in. So let's do our first trial here and see if this thing even fits. Let's get it over here. Look at that. Kind of looks like it was made for it, huh? Let's put our other one in on the other side. The other thing I did on this one was the other board, the original board, only has terminals on one side. And these little sockets, the way they're shaped, I don't know if you can see that, they're kind of shaped like this. So the board kind of plugs in between, so you actually have contact all the way around. So what I did was, let me back up, I actually plated both sides of these with terminals and then used little tiny mini vias. I don't know if you can see that, if it'll focus, little vias to connect them together so you get really good contact. So, and it fits really well, surprisingly. This all kind of was guesswork, but there it is. Now I'm going to have to make some kind of a bracket to kind of stabilize these on the top. I'm not sure what I'm going to do yet, but I'll figure something out for that a little bit later. But for right now, there it is. I guess the only thing left to do is try it. So before I put this amplifier together, I powered it up on a dim bulb and made sure that there were no shorts and there were no wiring errors and that the power was correct and that these transistors were properly mounted, didn't have any shorts, they were all connected, and we had no problems. So we know without these two boards plugged in, the amplifier draws very little current. It charges the caps up and it does what it's supposed to. So I kind of repositioned the camera hopefully to get this all in shot. Here's the amplifier. Here's the dim bulb, and I have never plugged this in yet with these boards. This is the first time we're going to check it together. If we have a failure, we're all going to experience the failure in real time. So here we go. That's a good sign. See how the bulb went real bright and then it dimmed? Now, without those boards, the bulb was very, very, very dim. It almost went completely out. And now you can see it is glowing slightly, so there is quiescent current going in there. So, smoke. All right, where's our smoke? This side is cool as a cucumber. This side cooked. So let's see what we have. Something burned. Question is, now this is warm. The other side did fine. So where did the smoke come from? We all saw it, but nothing looks burned or discolored. You guys are seeing on the camera, and I'm looking around the camera, so you probably have a lot better view of it than I do. But I do not see where the smoke came from. It's that phantom smoke again, isn't it? Maybe it was not the board, but I have a feeling it was. Anything on the back of the board? I don't know, guys. Do you see anything? I don't. Let's give it the sniff test. Nothing smells burned on this. So maybe the smoke came from down in here somewhere, from one of the transistors. Now we had everything on the dim bulb limiter, so whatever it was, it probably couldn't have cooked too much. But let's take the bottom off and see what it is. I don't see anything wrong on this. And this got warm, but it didn't get super hot. Okay, a couple tests, and we'll be back. Well, problem solved, I think. So first of all, let me bring you over to here. And of course, it is a Tony-induced problem. I told you, no matter how many times you check things, you just never know. So let's zoom this in. And if you look here, we have pins 1, 2, 3, 4, 5, 6. Wait a minute. 1, 2, 3, 4, 5, 6. Pin 7 is this black and white wire, and pin 8 is this yellow and white wire. However, if you look on the schematic, let me get you down here. With the bad lighting, the yellow and white is supposed to be pin 9. So basically what we did was we took this line and connected it down here, which is why you're putting your 35 volts right through that 100 ohm resistor up to here. No wonder it shorted out. And that's what was getting hot, was this little resistor. And there it is. And on the board, that resistor was located right here, which I swapped it out. And it's resistor R37. And R37 is right there. You see it? And I checked this transistor. I pulled it out of circuit and tested it. It got no damage at all because, of course, the wire, it didn't hurt anything. So the only thing that got damaged was that resistor, which I replaced. And the reason the other channel didn't burn up is because, if we look at it, you can see pin 1, 2, 3, 4, 5, 6, 7, 8 is this wire. 9 is this wire. So basically these two wires are moved down one terminal on the other channel, and that's what caused the problem. Now hopefully with these big heavy output transistors and everything, we didn't cause any damage. I really doubt that we did, but that's where we are. So let me move those two wires and fix my Tony problem. And then we'll come back and see if it still smokes. Okay, the two wires are now moved into the correct position. And hopefully this will all work now. We're going to turn it on, and hopefully this will go dim. And after the caps charge up, and we should have a very low current draw with this thing sitting idle. So let's plug it in. I have the meter. It's not connected to anything now, but we're going to check our plus and minus 35 volts. Now they're going to be low simply because we have that bulb in there. But we should see somewhere between 25 and 30 volts, I would imagine, depending on how much the bulb attenuates. So anyhow, let's plug this in and see what it does. Okay, and it pulsated a couple times. That was the protect circuit on those boards. And notice the bulb went completely out. So that's what it was doing without the boards plugged in before. And you can see we have, let's see, we have minus 35. Wow. And plus 35, or I'm sorry, yeah. So we have our plus and minus 35 volts. How about our 90 volt supply? Our 90s riding pretty high right now. So, but no smoke, very low current draw. Let's hook up some speakers and put a little signal in it and see what happens. Okay, amplifier's powered up. Dummy load is connected. Signal generator is set to 1 kilohertz, and I'm going to drive it with 50 millivolts input signal, because if you go too much more than that, the bulb's going to start taking up the slack. Plugged into both inputs, and let's zoom in on our scope that's in its new little home there. Makes it a lot easier for me to get a good angle on it. I'll shut off this light. There we go. Do you see how that light affects the scope? So, okay. Signal generator on. Oh boy. And of course our dim bulb is really going kind of lighting up now a little bit because it's drawing current, but our boards work. Yay! Yeah, okay, I'm really excited because I really didn't expect that. I did not think it was going to work right out of the box. I truly didn't. But as you can see, it works, and that was with only 50 millivolts of drive signal. Of course, we're going to have to let this thing off the leash and get rid of the dim bulb if we want to test it any further. But it works. Okay, we got the amp sitting up and it's warmed up now. And the heat sinks are ice cold. And I've been running this thing on and off for a good bit now. And I mean, literally, these are the same temperature as the chassis. They're not even getting warm. The only part that heats up on this amp is this 5-watt resistor, and it gets really, really, really warm. It's not burning up hot, but it's hot to the touch. I mean, I can't hold my finger on it for very long. It's too hot. So that really should be more like a 7-watt or a 10, even 10-watt resistor to run a little bit cooler. I may make that change. But just to give you an example how this thing's working, it still needs some refinements for sure. But this is where we are so far. We'll come in on the scope, and we'll watch the RMS there. And I'm going to add another measurement. There we go. So there's your frequency. So channel 1 is your output voltage and your frequency. And let me turn it on. And you can see how clean that is. And look, 15 hertz. And I got 28.2 volts. And you can see how clean that is. So if you take, we'll do the math here. 28.2 squared divided by 8. There's 99.4 watts. And of course this will do about 100 watts. It's rated around 100 watts per channel or so. And it's doing that very well. 20 kilohertz. Let's go up to 20 kilohertz. Now I'm going to drive the same signal into it. And I don't know where I need to be here, but you can see 27.8 volts. That's at 20 kilohertz. And again, pretty flat. Same signal level going into it. I have not put the distortion meter on it yet, although I do think this amp does have just a little bit of distortion. I think there is a very slight crossover distortion that's being generated, not in the output section, but somewhere around the driver section. I'm going to have to look into it. Maybe not. I don't know. Maybe it's supposed to be that way. But the output looks very clean, as you could see. It was extremely clean. So I would say this amp's working. one of the big main filter caps was acting a little bit funny. It still is, I think. It doesn't affect the circuit, but one thing it does not like, if you plug this amplifier does not have a power switch on it. So if you look on the front here, and you look, there's no power switch. So basically when you plug this in the wall, it turns on. And one thing I'll tell you, even with those thermistors in there that they put in there, when you plug this into the wall, this transformer goes crazy because these capacitors really put such a load on everything. And when these things come on, they come on so hard that it actually affects the clipping circuit on these boards. When the clipping circuit activates, it shuts down the amp and then turns it on rapidly, like on and off a couple times as the capacitors are charging. And that shocks the system even harder, because then you're drawing excessive current and you can blow the fuse on it. The other thing is, I noticed, if we look at our power meter, remember this thing's rated for a 5 amp slow blow fuse, and I'm going to leave this thing right at that 100 watt range at 20 kilohertz. It doesn't matter what frequency, but upper right hand corner, so right here, that's your current. Let me turn that. Now the idle current's very low, it's 300 milliamps. But when I turn this on, you can see at maximum wattage it's drawing about 4.3 amps total. Now that's for both channels to get your 200 watts, but that's a substantial amount of power. And you could see they put that fuse in there. That's why they want a 5 amp slow blow. They literally have that fuse set right on the edge of what the maximum of this amp is going to be when it's running continuous power. So it's important to have the correct fuse. I do not have a 5 amp slow blow in there right now. It's a fast acting fuse, and if I push this thing too hard, it will open the fuse probably. It won't vaporize the fuse, but it'll open it. But our little board works, and I'm still kind of surprised at all of that. I don't know. Other than miswiring that one socket, everything else looks okay. Now we're definitely going to have to do a few more tests on this thing over time, but these are ice cold. I mean literally ice cold, and I don't have to worry about touching the heat sinks together and getting shocked or anything, because again, all these transistors are up on insulators now, as are these. And again, this is just barely warm to the touch. It's warm, but just barely warm to the touch. Like I said, the only thing that's hot is these resistors. So I'll probably change those. Anyway, we're coming along pretty good here. Well, this thing's been going for quite a while now, and I am thrilled. I just can't believe this stupid thing works. I just thought for sure that there'd be more smoke than we got. One little resistor we sacrificed, that's it. So this thing's been on. I've been playing it just from this little cell phone, which does not have very good equalization, so the sound is not real well balanced, but it gets pretty loud. And I've been playing it, and just to give you an idea, there's the heat sink, there's the other heat sink, they're within 1 degree. We'll switch it to Celsius. You can see nothing. I mean, it's room temperature. Now this resistor, on the other hand, a little bit warmer. And the heat sink up here is just slightly warmer, but not at all, hardly. I don't know if you can see that. Same thing over here. I mean, they're all running about the same. They're not getting warm. This amp is just the coolest running amp I've ever seen. And it is absolutely dead silent. There's no hiss, there's no hum, nothing. So, I don't know what to say. Not much to do on this video, because I basically put the board together, plugged it in, and it worked. I'll do one final look at the underside before we put the cover on. And no, I haven't fixed the cover yet, but when the weather gets better, maybe I will. And I mean, everything other than replacing the can capacitor in there, everything else is pretty much stock. You know, I kept it the same. Moved a couple of terminals around to make the wiring a little bit more sensible, and to bring the grounds all kind of into a star ground system. And that worked, because this amp is absolutely dead silent. But there it is. It's all together, including our rewired, miswired connector over here. Not bad. Sweet. And there she is from the top side. She's a survivor. And yep, I left this alone, but I am going to finish this. I'm going to, you know, strip the paint, sand it down. I'll repaint it. I'm probably going to put some wooden sides on it. Maybe replace the logo. Do something whimsy. I don't know. Who knows? But all in all, and you can see I replaced these resistors with 10 watt. They look kind of out of place there. I'm probably going to make a mod to the board design with 2 holes. One hole for the 5 watt original, and then another set of holes, you know, just further apart, still tied to the same place, to put this optional 10 watt resistor in there. I think it runs really cool now. It doesn't even, it just gets warm. The amp runs really cool. And you can see, even the back turned out pretty good. I mean, I can't complain. And there's the transformers with all their scars, but it doesn't look bad, considering what it looked like when it came in, I guess. But there it is. So I want to do a couple of final comments on these boards here. A couple of changes that I'm going to make. First thing I'm going to do is I'm going to make a provision, because we have all the space along here, to put that 10 ohm resistor in, or the 10 watt resistor instead of the 5 watt. So I'll leave this pad here so that you can use this, because it does work. They just run really warm, too warm to hold your hand on, and that to me is a little bit too much, even though it'll work. And then I'm going to add a second pad up here to be able to accommodate a 10 watt resistor if somebody so desires to do that, or if you want to do that in the future. The other thing that I noticed is when I designed this bottom part, there was no footprint for these connectors here at the bottom for this type of Amphenol edge connector. So I had to kind of make this one using the footprint editor, and this is new. I've only made a few different boards where I've actually created the Gerber files and everything, so this is totally new to me. And it was kind of difficult for me to figure it out, but I got it figured out. But one thing I noticed is when I did the edge cuts, where you define the edges of the board for the diameter when they cut it, this is just a little tiny bit too narrow. Probably I need to add about 1 to 1.5 millimeters on each side of this board, because what it allows right now is it can actually go this way back and forth inside the socket. So you kind of have to make sure you get it lined up with the pins when you plug that into the socket with this board the way it is right now. If these were about 1 millimeter to 1.5 millimeters wider on each side, that would prevent that wiggle room and allow it to line up a lot better. It doesn't hurt anything, it's fine, but you can push it extreme to where the pins are almost not touching at the edge, which that's not good. Some other things to note. I heard a comment about these bias diodes here needing to be coupled to the up here to the heatsink. That would be a really good idea, but from what I recall on the original design of the board, instead of coupling this to the heatsink, they actually put this diode on the underneath of the heatsink on the other side of the board. So it really isn't thermally coupled to the heatsink. The only way they could have done that would be if they would have mounted it and then put that square heatsink on top of it, which every photograph I've seen of that board and what I remember of the one that I worked on in the past was that that diode is not positioned there. But I could be wrong, so correct me if I'm wrong. But that might be a good option in the future, maybe to relocate this. You could kind of maybe epoxy them, or with thermal epoxy or something to the heatsink, and then run the wires down to here. But so far this one has worked extremely well. The amp is running really cool after being on for long periods of time. Running it right near its 100-watt limit, near clipping, it doesn't seem to heat up hardly at all, maybe a little bit. This heatsink up here gets just barely warm. So I just can't, and the waveform stays really clean. We don't get any distortion. So I really don't think that thermal tracking is a big issue with this board design. But again, time will tell as we use it more. Again, I used all 1-watt resistors in here, and I used metal film. Some people will argue that the film resistors, because they're spiral cut, that spiral cut has some inductive reactance to it, but it's at extremely high frequencies, and this amplifier is really not going to be anywhere near that. It doesn't have any problems with the oscillation or anything like that, so I'm not really worried about it. Metal film resistors are a lot more durable than carbon composition resistors, which is the original type that they used on these. They're just more durable. They don't drift. You can abuse them a little bit. In other words, if you overload it because something shorts out and they get real hot, they tend to not drift as much when they're overheated. Anything can be damaged, but so that's why I use that. And I used the 1-watt resistors simply because modern film resistors are physically smaller. So a 1-watt metal film takes up about the same space as a 1/2-watt carbon comp resistor. And that's, so I use the little bit bigger resistors. They fit in here. And you can put smaller ones if you want, but it worked really well. I did use a 2-watt up here for this 22 ohm, which is the resistor that connects to the collector of this transistor here. I'll show it to you real quick. That would be for this resistor right here. And if this one goes, you can have all kinds of problems with taking out stuff over here. So you want this to stay really stable. This should be the last thing that goes out on these if something fails. And then this is that 5-watt resistor, and you can see this is setting up like a current source for this and so forth, and it gets really warm. So again, there you go. So those are some notes about this. I'm pretty happy with it. I can't complain. So like I said, we're going to try to do some music with this and listen to it, see what it sounds like. And, oh, I wanted to talk a little bit about these autoformers too, because there's been a lot of comments on those. Let's go over that. First of all, I want to focus your attention on the little schematic on top of the transformer. If you notice, this transformer has no secondary. It's just a single coil. It's a tapped single coil. So if you notice, you have your common, which is going to go to ground. You have what's called the input. This goes to the output of your output section of your amplifier. So this connects to the actual amplifier's speaker terminal output. And then you have 4 ohm, 8 ohm, and 16 ohm. Notice this tap is below 4 ohms. That's really critical to the design of this amplifier. And let's go a little bit over how I understand this idea and why McIntosh designed it this way. The whole purpose of this, and here's your transformer in the circuit in the schematic, the whole purpose of this is that they designed this amplifier to be approximately 2 ohms stable. In other words, it's designed to work at its optimal performance at around 2.3 to 2.5 ohms of impedance. Now we know speakers have reactance, so they don't always produce the same, or they don't always present the same resistive load to the amplifier. Because you have changing voltages, you're going to have changing resistances because of the reactance. So if you look up reactance if you don't understand what I'm talking about. So the idea that behind this is, if we always present as if there is a 2 ohm or 2.5 ohm speaker connected to this, no matter what type of speaker load you connect, this amp will always work at its optimal performance. So by having this in here, this adapts the impedance of your speaker to the desired impedance that the amplifier wants to see. And that's really important. Going back to the power supply, remember this thing had those huge 39,000 microfarad main filter caps. That was not by accident. This amplifier will always have a maximum output of around 100 watts per channel, regardless of what load of speaker you connect. So you can put a 16 ohm speaker on this and it will still deliver a full 100 watts to that speaker. How does it do that? By using this transformer, it's going to draw extra current through this circuit, but it is going to use that current to convert it to the extra voltage you need, and vice versa, so that you always get 100 watts of output regardless of what tap you connect to. Could you connect a speaker directly to this and eliminate this? Absolutely you could. But what will happen is the amp will not work at its optimal design point. If you put an 8 ohm load on this and you don't have this transformer, you probably will not get the full 100 watts. If you put a 16 ohm load, you definitely will not get the full 100 watts because it's a voltage divider, right? If you increase the resistance across there, then the amount of current that flows through that resistor will go down. Because the resistance went up, the wattage is going to change. That's why if you connect a 4 ohm speaker, it would be closer to that 100 watts. If you put a 16 ohm speaker, it would be further away from that 100 watts. But with this transformer, regardless of that, this coil is matching the impedance to the speaker. So if you look at one of my previous videos I did on signal generators for people who wanted to do tuner alignments on tuners, if you recall, I had shown you a couple of devices to be able to match a signal generator that needs a 50 ohm load to have the correct output to a tuner that only presents a 300 ohm load. So of course your signals are going to be all wrong because the impedance matching is wrong. And we used a special little transformer circuit, or an impedance matching circuit, to fix that. This works on that same principle, really. That's what this is. And so there's all kinds of arguments that putting this in there colors the sound. I have not seen nor heard that. It just doesn't. It's very transparent in my ears anyway. And if you actually took a meter and just statically measured the DC resistance, you'd find that it's very low on this transformer. So, even things like damping factor and everything are not as big of an issue as you might think. So this was a carefully designed and thought out product by McIntosh, and it works. One of the drawbacks is these transformers, in order to deliver that kind of power, have to be very large, as you see they are. And that kind of iron and that kind of copper is very expensive to manufacture. This is not just a piece of wire wound around a core. It's actually bifilar. In other words, there's multiple windings that are connected together internally, and when it's done electronically it looks like this, but there's a lot more going on inside that transformer than just a piece of wire wrapped around a core. So that's another thing you need to look into, is how McIntosh winds their transformers. They actually, I believe, had patents on that type of transformer winding. They may still hold those patents, I don't know. But anyway, that's a little explanation of how this works. So with that in mind, let's try to listen to it, and really the proof's in the pudding, right? It's all how it sounds. The rest of all this theory means nothing if the amp doesn't sound good. So that's what we want to see next. Okay, we have something cobbled together here. I'm just using this old Adcom preamp, and I'm just connected up directly to that from the little digital music player. And we are using the Klipsch speakers, the reference, what is it, 6.5 or something? I forget the model number. And Bella is going to assist us. And if you hear her in the background, well, she apologizes in advance. Huh, Bella? What? What? What are you telling everybody? Are you twirling? Oh my goodness. Sit down. Sit. See how good you listen? There you go. You listen better than the rest of the kids, huh? Okay, well, and you can see over here the messy living room getting ready for Christmas and everything, but here's the recording device, and it's kind of sitting across from the speakers, which are here, and we'll get started. And you'll notice one of the songs that I play is very, very poorly recorded. It's because the song is over 30 years old. It was recorded on an old cassette, like standard cassette type 4-track Yamaha cassette recorder by, up in my bedroom with myself and a friend of mine playing guitar. It's a very old song that we recorded for a contest. It's a cover tune of a very little known band called, the name of the band I believe was Another Carnival, and I think the name of the song was Still. At least that's what I think it was. That's what I named it on the MP3. And I found the cassette, and I turned it into an MP3. I recorded it, digitized it on the computer. So it's very poorly, the tape is very old, very muffled. Any of you know about recording with 4-track decks? Anytime you have multiple tracks and you have to bounce tracks back and forth, you lose, you have degradation. Not to mention 2 kids playing music in their bedroom. So I guess this is a lesson in humility for myself. I thought I'd play for all of you. And okay, let's go on with it. And that's it. We're getting ready for the holidays now. I'll end this. I hope you all enjoyed the video. I sure enjoyed all of everybody's comments and all the emails and everything I've gotten over the last month or so. I appreciate all of you, and I thank you all. I wish you all a happy holidays, Merry Christmas, all those things. And until next time, we'll see you soon. I wish you all peace, joy, happiness, and good health in your lives. And we have lots of things. The next project that's coming up probably next week is a really cool one. Something that I've been kind of putting off and decided I wanted to do. It's nothing really a big project, but it's just something I think some of you will be interested in maybe making one for yourself. So, with that in mind, I wish you all well, and we'll see you all soon. Take care. Bye-bye.